Hi everybody, this is Mr. Mitchell again with another video. Today we're going to talk about oceans, water, currents, and waves. You know, ocean water is much more than just salt and water. It has many different dissolved substances in it besides salt. The ocean contains some of every element known to man. Now, you haven't studied much of the periodic table here, but every natural element known to man is number 1 through 92, and bits of every one of them have been found there, from aluminum to silver to uranium to hydrogen. There should be helium up here. I'm not sure why it's not there. But the sea really has so much besides just salt. For every 1,000 grams of sea water, you have about 35 grams of salt, which is 3.5%. Now, it's not going to be 3.5% every place in the ocean. We'll find out later which places are saltier and which places are not. How salty the water is called salinity. Salinity. And the 3.5% is the salinity, average salinity of the ocean. Salt water is more dense than fresh water. It's heavier, and things float better the saltier the water is. And you can see these two fellows. These guys are floating in the Dead Sea. It's very, very high salt content in the Dead Sea, which is off in the Middle East, and it's so salty that no fish can even survive there. Saltier water is found where there is ice, quickly evaporating water, and you can imagine why. Because if there's ice at the surface, the fresh water freezing from there, so the remaining water would be saltier. And where it's evaporating, you have fresh water leaving the ocean, which means that it would be saltier there. So really hot places have a chance of having quickly evaporated water that will leave saltier oceans. Now, the less saltier places of the sea are where rivers empty into it, and that makes sense. You have a bunch of fresh water coming in, mixing with the salt. And where there's lots of rainfall, you have fresh water falling into the ocean, mixing with the salt. We'll click to the next slide. Oxygen is one of the elements found in water. And just like human beings, ocean animals take in oxygen, except the oxygen is dissolved in the water. Do they give off carbon dioxide just like we do? Yes. And it is carbon dioxide not in bubble form, but it's carbon dioxide that is also absorbed in with the water. It's mixed in with the water. You don't see it in bubble form. It's dissolved. That's the word I'm looking for. And you can see that we have underwater plants. We have the carbon dioxide that is exhaled from the animals, taken in by the plants in dissolved form, which gives out oxygen in dissolved form, which is taken in by animals. So it's just the same symbiosis that we have here on land about oxygen and carbon dioxide. Now let's talk about ocean currents. Here we have a chart of the ocean, the known ocean currents, and you can see they have directions. We have talked about this Gulf Stream ocean current here. They have the arrows pointing where the directions go, and there actually are some patterns here. Now, these surface ocean currents are just in the top 300 to 500 feet. Now, you may think, well, that's a very deep amount, but I mean, you take a look in the middle of the ocean, and sometimes it can be miles deep. So 300 to 500 feet is just really the surface of the ocean. These currents move warm water, like the Gulf Stream does, moves warm water away and spreads it out toward the northern areas. and that will make things warmer. I think we've mentioned that this Gulf Stream ends up traveling up through here and makes Europe a little bit warmer. And cold water currents will take cold water and disperse it down from the North Pole and up from the South Pole. So these currents disperse all this warmth and all this cold. It makes it to where it balances out a little bit. Outside of the Gulf Stream, one of the most famous currents is the East Australian Current, made famous, of course, by the movie, where you had the East Australian Current and the fish and turtles darted inside the current. Now, if you notice, these currents have a direct pattern to it. Look what we have here. These currents go in a counterclockwise direction, but they go in a counterclockwise direction only in the northern hemisphere. In the southern hemisphere, look at the direction they're going. They're going in a clockwise direction. You know, I said that completely wrong. In the northern hemisphere, it is clockwise. This is how the clock goes. But in the southern hemisphere is where it is counterclockwise. You see it down here as well. And what that tells scientists is the reason we have these currents is because of the rotation of the Earth. Think of it. I mean, if you have this big ball with sprays of water on it and it's spinning, that water is going to move. So because we have the rotation of the Earth is why we have the winds that make the currents move. And that's why you have currents, because of the rotation of the Earth and the wind that comes from it, and the wind pushes this water along. So that's why you have currents, rotation of the Earth and the wind that comes from them. There are some deep currents, like below 300 to 500 feet, but they're not as predictable where they would be. They mostly are from moving or from sinking water that was already in one of the bigger currents. Sometimes surface currents affect the weather patterns. I have this next chart here. You may remember we talked about El Nino. Normally we have this Peruvian current that comes here, we have wind that comes this direction, but we have weather that sometimes comes from the opposite direction. So whenever you have, for some reason, less strong winds and less strong current, it means the weather hits it a little bit harder. From what I understand, El Nino can hit a little bit harder in South America than North America, but kind of the same thing. You have these currents which are kind of rotating around like this up here, and the winds which are the same thing, and whenever they're a little bit less, that's when you would have some more severe weather potential. About every 3 to 7 years is when an El Nino year happens. Waves transport energy. Speaking of waves transport energy, not water. Now sure, this water that's right here on the top of this wave, sure, it will be pushed a little bit inward, but for the most part, the waves just go through and the water just goes up and goes down and up and down and up and down. And think of this bob here. Sure, the bobber is going to be gradually pushed this direction, but for the most part, the wave comes in, the bobber goes up at the top of the wave and down at the bottom of the wave. Up at the top of the wave, down at the bottom of the wave. You have mostly just energy and not really much transport of water. Water generally stays in the same place. Now waves lose their energy when they break onto the shore. There is something called an undertow. Those of you who have been to the beach may have felt the undertow. The undertow is the pull of water as it runs back to the sea. Now this is probably not sea here, but you had waves that come into the sea, and as you're out here standing in the waves, you have this undertow which kind of pushes your legs back toward the sea. And sometimes undertows are bad enough just to take swimmers out to sea. So you kind of have to watch for the warnings on the undertow. Also, there are longshore currents. You may remember this one. We talked about it before. Here we have the beach. The longshore currents run along the shore. Longshore currents run along the shore. And I misspelled longshore. Should be a G right in here. Sorry about that. And then there's something called a rip current. A rip current looks like this. Here we have a sandbar. Sandbar that's under the water here. And whenever the waves end up breaking through the sandbar, if a person's here just a little bit out onto the beach, I guess out from the beach, I guess maybe out in the water a little bit, if they happen to be standing here whenever the sandbar breaks, the water flushes quickly out to sea. And as you can see from here, the way to escape is not to turn and swim against going straight back to sea, but to go out to one side. It says you can escape here, you can escape in several different ways, but is to swim parallel to the shore. So if you happen to get caught in a rip current, that's something you do. These rip currents are caused by the waves, even caused a little bit by high winds, and they're dangerous for swimmers. I think your book is going to say that there are a lot of people that have to be rescued because of rip currents, and it kind of surprises people, as you can imagine it would.